So section 5.5, linearization of differentials. I will say that there are 3 key topics that we're going to hit today that you need to understand well for the rest of the year. So those key topics are listed in here, and I'm going to focus on linear approximation, very important, differentials, very important, and then we'll do some work with differentials, and then Newton's method. Those are the 3 key things we need to get through today. Okay? So, linear approximation, also called linearization, is what we've been doing since the beginning of the year. If I have some function f of x, and I am interested at some point A, then I could write an equation of a tangent line, which we've been doing all year. And if you will notice, this tangent line, as long as I stay very close to x equals a, is a good approximator for that function, right? The y value on the tangent line is very close to the y value on the function, as long as I'm really close to that point of tangent. What happens if I move further out in the x? Is my tangent line a good approximator as I move further out? No, because the y value, you can start to see the disparity. The y value is here for the tangent line and up here for the function. So it's only a good approximator of the function if we stay very, very close to the point of tangent. Now, why do we do this? People ask me all the time, well, why don't I just use the function to find the y value? Well, sometimes we have data and not an actual equation. So we have a model of a graph without an equation, and the tangent line would then be able to approximate what the y value would be close to that point of tangent to be. Sometimes the function is kind of ugly to work with. Maybe we do have the equation, but it's very difficult to work with. A line is very easy to work with, and we can find y values on a line very easily. So, take a look at this picture. We have the point A, f of A, and let's make sure we understand what is written down here. The tangent to the curve y equals f of x at x equals a is the line y equals f of a plus f prime of a times x minus a. Where is all that coming from? Where is that information coming from? Manat?
Well, the f of a comes from the y.
F of a is just the y value, right here. Yep.
Then
Okay.
after that, you basically multiply slope times the difference between the exponential function and the straight line.
Between the function f of x and the straight function, the x values. But this is just another form of what down here? Point slope. It's exactly what we've been doing. My pen keeps dying. It's exactly what we've been doing to write our equations of lines. Y minus y1 equals m times x minus x1. And all I've done is solve for the y. This is our f of a. Try one more time. Sorry, my pen is dying. Okay, our f of a is just our y1. Our f prime of a, well, that is the slope. And when we write the equation of a tangent line, we use the derivative to find the slope. And this x minus a, what's a? X sub 1. It's just point slope solved for slope-intercept form, solving for y. Okay, so it's exactly what we have been doing. Okay, so let's look at what we have. This is just, I only put this on here because there's some terminology that we just need to be familiar with. This L of x is our equation of the tangent line. equation of the tangent line. And as we said, it's just point slope solved for y. So it's exactly what we've been doing. Defines a linearization of f at a. So finding the equation of a tangent line is also called doing a linearization. And the approximation f of x is close to L of x is called the standard linear approximation of f at a, and the point A is said to be the center of the approximation. And again, I only put this up here because this text uses these terms, so I want you to have seen them. Okay? Okay. Let's look at an example. All right. Oh, geez. Okay. Not an alarm. Not an alarm. All right. Find the linearization of f of x equals the square root of 1 plus x. At x equals 0. And use it to approximate the square root of 1.02. Then use a calculator to determine the accuracy of this approximation. All right, so let's write an equation of a tangent line using this information. So what do? We will find the derivative, but what's the format I want first? Y minus y1 equals m times x minus x1. All right, and let's find out what we have. Y minus, do we have y1? Can we get it? Y1 will equal what? The square root of 1 plus 0. Just 1. Y minus 1 equals, m we'll worry about in a second, times x minus what? 0. Okay? All right, and now, Ashley, how do I get my m? I get my derivative, thank you. All right, so here, my derivative, f prime of x, is going to be 1/2 times 1 plus x to the negative 1/2 times 1. Do I put it in the equation in this form? Nope. What do I do? Maybe. I put in 0. Yes. We're interested at the point x equals 0. So we have 1/2 times 1 plus 0 to the negative 1/2, giving me what? 1/2. So there is my equation of the tangent line, which is y equals 1/2 x plus 1. You don't have to move it to slope-intercept form, but we will in this case, just to make it easier for us to find our y later on. Okay, then it says, use it to approximate the square root of 1.02. So I have my L of x, as they refer to it in this book, is y equals 1/2 x plus 1. And I want to use that to approximate the square root of 1.02. Well, what is my x then? Take a look at our f of x. F of x is the square root of 1 plus x. So this is the square root of 1 plus 0.02. So we are looking for the square root of 1 plus 0.02. So our x is 0.02 in this case. And then we can just use this line to approximate the y value. Y equals 1/2 times 0.02 plus 1. And we get what? 1.01, yes. Okay. All right. So that's what we get for our approximation. And now it says then use the calculator to determine the accuracy of the approximation. So on all of these, we're going to be finding the error between the approximation and the actual. All right? So if we're looking for error, we're going to do the absolute value of the original square root of 1.02. Is that right? Yes. Minus 1.01. Find that difference, please. And tell me what we get. Everybody's calculator should be out. You're going to need them the whole time today. What do we get? 9 point something. 9 or something. Oh yeah, sorry, I'm reading my own writing wrong. 4.95? 0.95 times 10 to the negative 5. And the way that they like you to present your error in this book is that the error, oh no, that's not right. Error is less than 10 to the negative 4. So you go up an order of magnitude, and we are guaranteed to be less than 10 to the negative 4. Okay? We can say it's less than 10 to the negative 5 because we're already bigger than 10 to the negative 5. So the error will be less than 10 to the negative 4, just to get a nice round value. Okay, questions on this one?
Where did the 1.01?
The 1.01 came from plugging 0.02, our x value, into this equation, into our line equation. So we get 1/2 times 0.02, which is 0.01, plus 1. So we're using the tangent line to approximate this value. You need to plug into the tangent line. And the x value is 0.02 because our function, f of x, was the square root of 1 plus x. So if we're trying to figure out the square root of 1.02, that means that the x value is 0.02. Yeah? Next.
How do you drive that error? Why you do this?
Yeah, so all we have to find is how far we are off from the actual value. So our calculator can get the actual value, the true value of the square root of 1.02. We're subtracting what we got. That difference is how far we are from the actual value. Okay? And it wouldn't be wrong to write 4.95 times 10 to the negative 5, but the general convention for this book is to get a nice round number, go up an order of magnitude, and then say, well, we're guaranteed to be less than that. Yes?
So I'm asked to do that, is 4.95.
Depending on how I say it, yes. I would like you to deal with this. I would prefer you did it this way, because quite often on the AP test, they show that the error is less than 10 to the negative 3, or something like that. So just working with this general 10 to the negative format, you'll see more often. Okay? Anything else on this one? Okay, let's move on. Do this one now. Same type of problem, you do it on your own, please. All right, does anyone have the equation of the tangent line? Yeah, Jackie?
What's going for?
Oh, let's start with point float one.
Okay, so y minus 0 equals negative 1 times x minus pi.
Very nice. Go ahead and solve it. Well, it is solved for y, so that's easy enough. So we get y equals negative x plus pi half. Okay. And then use it to approximate cosine of 1.75. So what do I do now? What's my x value? It is 1.75 in this case. So y equals negative 1.75 plus pi half. And we get, I don't know what, negative point, give me 3 decimal places. 179, is that what you said? Sorry, I thought I just heard 79, but 179. Negative 0.179. And then use your calculator to find the error, to determine the accuracy. So our error is going to be the absolute value of what? Cosine of 1.75 minus negative 0.179. And I get something like 9.576 times 10 to the negative 4. So our error is guaranteed to be less than what? 10 to the negative 3. So, okay. All right. Questions on that one? Yeah, next.
Can you explain how you got y minus 0 equals negative 1, x minus
You bet.
half?
So they gave us an x value of pi half, right? So x equals pi half. We need to plug that into the original function to get the y.
Okay.
So that's where our y is coming from. Y equals the cosine of pi half, which is 0. And then the slope, m, is going to be the derivative of cosine, so that's negative sine of x, and negative sine of pi half is negative 1. So that's where all the parts are coming from, okay? All right, anything else on this one? Okay, let's move on. This one, we're not going to have time to do. It's interesting, you can look at it in the book. I won't be testing you on it.
Wait, I got one question.
Oh, yes, sir. Back on that one?
Yeah.
Yes.
So, when we were calculating what, negative 1.75 plus pi half
Uh-huh.
equals, don't I have to do that without a calculator?
On this, you would have a calculator for that.
You would?
Yes.
Okay.
Yes, you would. Yes. And it would probably be to your benefit to, when you get your answer, we've rounded the 3 decimal places, but it would be to your benefit to store that in a variable in your calculator out to as many decimals as possible. And then use that as your subtraction, just to be more accurate. Okay? All right. Anything else? Yeah, Becky.
Why is the error less than 10 to the negative 3?
Well, because 9.576 times 10 to the negative 4 is less than negative 3, right? So if we have rounding error on this, we're still going to be somewhere in the 10 to the negative 4 range, and all of those are smaller than 10 to the negative 3. So we can guarantee we're less than 10 to the negative 3. Okay. Anything else on this? Okay. All right. Next, we're going to use it. This, I think, is a really nice use of linearizations or a tangent line approximation. That's the other way you'll hear this said, is a tangent line approximation. Use a linearization to approximate the square root of 123. All right, so before we had calculators, square roots were a more laborious task. You had to kind of work around it a little bit and do some interpolating to find out what the square root of a non-perfect square was. Okay, this is a nice way to come up with a very good approximation for a non-perfect root. All right, so the square root of 123 is pretty close to what perfect square? 120, that's a perfect cube, right? 121? Right, so if we say, let the function f of x be the square root of x, and let's say the point we're interested in is 121, comma what? Square root of 121, which is 11. So this is the information I want to use to write my tangent line. So we'll get y minus what? 11 equals, slope I always do last, times x minus 121. Okay? And to get my slope, I'll take the derivative, 1/2 times x to the negative 1/2. And what will we have there? This is 1 over 2 root x. And the point we're interested in is 121/11, so what will this come out to be? 1 divided by 22. Nice. Everybody okay with that? Well, how am I going to use that to help me find the square root of 123? Donna? Plug in 123 for x. Now our x value, the square root of x, our x is 123. So we're going to get y minus 11 equals 1 over 22 times 123 minus 121. Which is 2 over 22 or 1 over 11. And we get y equals 1 over 11 plus 11. And that is 11.0909, I think. Somebody check that for me. Is that right? Okay. All right. Everybody okay there? Okay. And now, let's see how far off we are from the actual. So, let's find our error. Absolute value of the square root of 123 minus this value. And give me our error. That's really not intended. What do we get? Sorry? Again, less than 10 to the negative third. The actual error we get for our calculation is what? 9 point? Oh, I'm on the wrong page. Heaven's sakes. I also got 3.725. times 10 to the negative 4. So again, our error is less than 10 to the negative 3. Okay? We're not going to do the next one, but you are welcome to go, these examples are in your book, so you can go back and look at that one on your own for a perfect cube. The process is exactly the same. Okay? Any questions on finding an approximation for a root? Okay, all right. Okay, now, so, first topic, done. Linearization. Second topic is differentials. All right, so what we need to realize is what a differential is. And if you think about the fact that dy dx, what's another way of writing that? Another way? F prime, yep. And that you're absolutely right with y prime also, but they use F here, so I'm going with F. F prime of x. So these two things are identical, yes? And they mean what? Derivative, which means what? What about the tangent line? Slope of the tangent line. So derivative is slope of the tangent line. So this dy over dx is a slope. And if you remember how we found derivatives in the beginning, it's the slope when we make our distance from our point of interest very, very, very tiny, right? So dy is a very, very, very small change in y, and dx is a very, very small change in x. So the dy and the dx are called the differentials. Usually if it's a big change, we write a delta. And if it's a tiny change, we write a d, a lowercase d, for the differential. So, if I wanted to find the differential dy, well, what would I do in this equation? You just treat this like an algebraic equation. Multiply by dx, yeah. So we would get dy equals f prime of x dx, which is exactly what we have here. And the differential dx is the independent variable. We're always told, or we figure, or we are given a way to find the change in x, and then we calculate the independent variable dy by plugging in our dx. Okay? So dx is the change in x on the tangent line. So if I draw one last picture for this. All right, we'll just go with that. Okay. We have some function.
The change on
Say that again?
the change in x on the left. Just here.
On the tangent line. On the tangent line. So I have this function f of x that looks like this. And I have a point of interest here at A. And I'm not going to try and draw this line. And I have a tangent line at A. Something like that. Okay? All right. And then what I am comparing here is I can move over some certain amount, dx, some tiny little amount in x. So this new x value would be a plus dx. And we had an initial point here that was a f of a. And over on the function right here, I have a point. What would that point be on the actual function? A plus dx would be dx, comma, f of x, f of a plus dx. Good. All right. And this equation of the tangent line, we're just going to call L of x, like they do in the book. And so what about on the tangent line? So at a plus dx, I'm actually here on the tangent line. And what is that point? Well, what's the x value? Still a plus dx. Comma. I labeled this line L. So we could call it L of a plus dx, right? Okay. So, when we talk about dx and dy, dx is the same for the function as it is for the tangent line. That distance is the same, right? Is the change in y the same on the function as it is on the tangent line? It is not the same. Could be very close, but it is not the same. So what we need to realize is that for the tangent line, our dx is right here, and this distance right here is the dy, the differential in y. So that's the change in y on the tangent line. And then what would I call this distance from here to here? That's on the function, not on the tangent line. So from here to here, that's just the change in f of x, or delta f of x. Could be called delta y as well. So that is the difference between delta y, which we've done ever since we started algebra. Change in y would be y2 minus y1, versus dy, which would be the change in y on the tangent. So that's a geometric or a graphical look at what we'll be finding in these problems. Okay? All right. So let's try a few examples. It says to find the differential dy and evaluate dy for the given values of x and dx. So we are going to be finding this dy, this difference on the tangent line, difference in y on the tangent line, given that our dx is this value and we're at that x value. So we said that dy is always equal to f prime of x times dx. All right. So given what we have here, dy will equal, what is f prime? So what's y prime in this case? 5x to the fourth plus 37. And we are interested at x equals 1, so y prime of 1 would be 5 times 1 to the fourth plus 37, giving me 42. So the f prime of x will be 42. And what is the dx? 0.01. So we get 0.42. So that means if this were my function and I moved over 0.01 units in the x, then on the tangent line I would only go up 0.42. Okay? All right, one more of these and then we'll look at different types of problems. So let's look at example B. Y equals sine of 3x, x equals pi, and dx equals negative 0.02. Find dy for me, please. So we found our y prime, we evaluated at pi, and we get negative 3. So dy will be negative 3 times negative 0.2 or 0.06. So if on this function, if I were to go left 0.02, my y change on my tangent line would be positive 0.06. Okay? So one use of these differentials, if you think about what you do in science, anytime you're measuring, you have some plus or minus error in every measurement you take, correct? And then, so if we measured a radius, and we were measuring with some tool, and we had plus or minus 0.1 centimeters as our error, and then we were calculating a volume. Well, that error now gets propagated into our volume calculation, correct? And there will be a consequential error on our volume, right? All of this can be calculated with these differentials. We can consider a differential, a tiny little change in some variable like radius, as our dr, and then we can use that to help us calculate what the differential in the volume would be. Okay? So calculus can be used to help us find the propagated error. So let's take a look at some example problems. Maybe just one. This we talked about. We should be okay. Yeah, let's look at this one. Estimating change with differential. So the radius of a circle increases from a equals 10, that's our starting, to 10.1 meters. Use dA, the differential in area, to estimate the increase in the circle's area, A. Compare this estimate with the true change, delta A, and find the approximation error. So we are dealing with area of a circle. So area of a circle is what? Pi r squared. Okay. And if I want the differential in area, well, we would take the derivative of area with respect to the radius equals what? 2 pi r. No rate with time this time, okay? We have no rates given with time, so I'm just taking the derivative of area with respect to the variable radius. And so if I want dA, then dA is going to be 2 pi r, and then the dr can come over. Will not be dr dt, but we're just separating our differentials. All right. What is r at our time of interest? What's our initial r? 10, right? So our r is 10. What is our dr? 0.1. The tiny little change in the radius is 10.1 minus 10 equals 0.1. Okay, and so now we have everything we need to find our differential in the area, which is, what we're doing is we're estimating the increase in the circle's area with the increase in that radius. So dA will equal what? What do I plug in? 2 pi times 10 times 0.1. Find a value for me, please. What is it? 2 pi or 6.28? All right, so we have used dA to estimate the increase in the circle's area. Compare this estimate to the true change, delta A. Well, how am I going to get delta A? Yeah, Ashley. Yes. Well, the first radius was 10, and the second radius was 10.1. So we can actually just calculate the difference in the two areas, right? That's the true change. Okay? And that's how we would find delta A. We would do pi times 10.1 squared minus pi times 10 squared to get the true change in what happens here. And find out what that is, please. What do we get? 315 maybe? Yeah, okay. All right. And then they said approximate the error. How am I going to find my error? Absolute value of 6.315 minus 6.28. And what do we get? 0.035, which is 3.5 times 10 to the what? Negative 2. So our error is less than what? 10 to the negative 1. Okay, questions on what we did there? The key thing is, here, we are using, in this portion, we are using the tangent line to approximate. Down here, we're using the actual function. And this is the difference between the two. Okay? Yes.
So you can just use the change in x values as the x?
Yes.
Okay, so
Yes. All right, anything else on this one? And remember that change in x, or change in r in this case, will be the same for the tangent line and the actual function. Okay. So, I need to get to Newton's method. So, just looking right here, there are different ways you can be asked to interpret change. And quite often you're asked to use the tangent line or use differentials to do these. The absolute change, which is our delta f, well, we just showed we can approximate that using differentials the way that we have been. If they ask for relative change, then you're going to take that value that we found up here and just put it in a ratio to the actual value, the function value. And then if we want percentage change, we take that same thing and make a percentage out of it by multiplying by 100. Okay? So different ways that they can ask you to discuss the change. Now, I am going to skip for now the changing tires problem, but I do want you to look at it tonight. I'm just not going to have time in class. So I want to get to Newton's method. I'll have this one up as well. Now let's get to Newton's method. The lab topic. So, take a look at the text here. You don't have to write that down. I'd rather you watch and understand what this means rather than writing a great deal. So it says Newton's method is a numerical technique for approximating a zero of a function using zeros of its linearization, or its tangent line. So if I look at the function we have here, the blue function, and I'm trying to approximate this root. Okay? And generally you're either given a range or you graph it and you see, well, it's somewhere between 0 and -1. All right? So we're given some kind of nice starting point. And what you will do is you will pick a value, an x value in that range, and use the tangent line root to get you an approximation of this root. Okay? So if I do that, if I use x sub n, and I make my tangent line and I find its root, I still have a pretty good distance from the actual root, correct? So I repeat the process. And I use this as my x value, and I go up to the function and I draw a tangent line there. And I find where that tangent line touches the x-axis. So I would come up here, and I would use that tangent line. Try like that. And I would use that root. Yes.
So is this kind of more like a trial and error technique?
The first step is. The first step is you're going to get someplace close.
Oh.
And then this process of using the tangent line x-intercept will get you closer and closer and closer. And when you start to see that the numbers are not changing much anymore, then you've reached your approximation of the root. Okay, so here, you'll notice that the x-intercept for this one is even closer to my root. Then I would go up and use that x value and draw another tangent line, and you would see that you would get even closer. So it's an iterative process where you keep finding the x-intercept of tangent line. Okay? So that's what's going on here. So you'll get the first approximation to a solution of f of x equals 0, and a graph of f of x may help. And use the first approximation to get the second. So then they just find this formula by plugging in 0 for y on the tangent line. They just plug 0 in here because that's where the x-intercept will be. And then they isolate our x. So it's just rearranging with algebra. So we can always get the next x value from the previous one. So let me show you the example for this one. So using Newton's method, solve x cubed plus 3x plus 1 equals 0. So we're trying to find the x-intercept. Sorry, the x-intercept, or the root. And if I were to do a sketch of this, it looks something like that. So again, I now know that my root is between 0 and negative 1. And it's closer to 0. So I'm going to pick my first x to be negative 0.2. And I can find my x sub n plus 1 by doing x of n minus f of x of n over f prime of x of n. So that's going to be x of n minus, what is my f of x? X cubed plus 3x plus 1 over what? Good. 3x squared plus 3. And all of these x's are actually little x of n's, because it's at the current x that we're interested in. So, here is the way I would suggest you do this. I would put this in y1. Okay? And I would find y1 of negative 0.2 to start. And I'll get a value for this, if I have it. I didn't write that value down. But once I find y1 of negative 0.2, then all I need to do is do negative 0.2 minus y1 of negative 0.2 to get the value. And what that is getting me is my x of 2. It's getting me my point closer to the actual intercept. Okay, so get your calculators out, please. What time am I at? Oh my God. All right, so you're not going to have time to finish. But does everyone understand what we'll be doing here? So then once I have this, and my x of 2 came out to be negative 0.3256. And then I go again to get x of 3. This is now my x of n. And I recalculate y1 of negative 0.3256. And I will do negative 0.3256 minus y1 of negative 0.3256 to get my next x value. And once I see those x values starting to look very, very similar, negative 0.3226537, whatever, where it's not changing much anymore, then there's your approximation for your root. Okay? I'm done. I'm sorry. I'm wrong. All right, so I'll get the extra examples up on the video. The homework is on the assignment sheet on the website.